How we doing, AP Bio fans? Let's talk about Chapter 2, Chemistry. Um, and here's what I'm going to say. You needed chemistry as a basis, and some of you are taking it concurrently um, to aid as a strong basis in doing well on the exam. You do not need to know everything about chemistry. I'm going to go through this rather quickly, but there's also we'll also be doing some stuff, and there'll be some added besides the study and reading guide that go with the text. I'm going to have put a couple things that I'm pulling together over what's important out of this chapter. Obviously, the basics of, do you know what an atom, do you know what a molecule, do you know what an ion is, do you know bonding? To some extent, chemical reactions, but really the reactions that we look at, condensation and synthesis reactions, or dehydration synthesis reaction type things, um, we'll see with carbon and macromolecules more so. But the understanding of how those reactions occur, so that you understand how these ions are moving in and out and doing the things that they do, and how things can get bound up and inhibit and do things, are important too. Have a little Billy Bryson short history of nearly everything. There may be days when we read excerpts from some of these books I have. Maybe if you're just bored, I'll do it for you. But anyhow, just pointing out, a couple hundred atoms in your body. For every couple hundred, most are hydrogen. Then the next amount is oxygen, then there's carbon, and of the remaining four, three are nitrogen, and the rest is divided among others. So what should you really understand? The atom's electron configuration, valence electrons, polar and nonpolar bonds, and electronegativity. And then the other weak kind of chemical bond forces and stuff. And again, what's an ion and how do ions form? That goes into the atom's electron configuration. So as far as biology is concerned, we really go with, just think CHNOPS of the elements that are used, and a little sodium, potassium, calcium, magnesium, chlorine and stuff. But carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are the big ones, and the basis for our macromolecules and other stuff. So just think CHNOPS. And of course, these are elements, not compounds. You should be able to read your periodic table and be able to calculate electrons, so atomic number, mass number, stuff you'll have to learn, and how to calculate charge from that. How do I know this is sodium? Number of protons and neutrons kind of thing. Negative signs, of course, are electrons. How can we predict the number? You assume that it's the same as the protons. The charged protons are positive. Neutrons are neutral. So remember, if I take an atom and change the number of protons, oops, went a little far. Then I have nuclear decay, because remember, an atom doesn't change its protons. If I change the number of neutrons, then I'm dealing with different isotopes of the same element. And if I change the number of electrons, I make it an ion. Okay, isotopes, ions, very important. Pardon me, a lot of talking today. Okay, so remember, your electron configuration helps you identify the number of valence electrons in the outermost orbital, and in a sense, what type of bonding it'll do and its reactivity. So remember your sp, d, and f orbitals and how many are in each, and how does that relate to the ionic charge, especially in the s and p. So a little reminder if you don't remember. And don't worry about drawing it. There it is. Full valence orbital, so non-reactive. All elements start out neutral. It's only when they gain or lose electrons that they become reactive. Okay, so a little quiz if you want. You can run through that. Try and remind yourself quickly, so quickly you can do it. Let's talk bonds. Reminder that covalent bonds, think of the words co and valence. Two or more atoms share valence electrons. Strong or weak? Generally, it's pretty strong. The more bonds they share, the less Flexible, the molecule is. Think double versus single, joining two arms with a dance partner versus one. Just because they share electrons doesn't mean they share equally. That's called polarity and electronegativity. What's electronegativity? Yeah, go back to polarity. What's electronegativity? Kind of like when a really popular person like me gets to the party. So there, I'm not there. There's the electronegativity. Everybody's surrounding me. What's the periodic trend? Where is the most electronegative, or what's the most electronegative element? Okay. Up and to the right should be thinking fluorine. Okay. So there's covalent bond. Hydrogen and oxygen in making water are sharing electrons so that you can fill out the oxygen valence shell and also for the hydrogen. Okay. All right. So this is a covalent bond. There it is. But because oxygen is so much stronger than hydrogen, it pulls the hydrogen electron more away from its sphere, doesn't completely drag it into the oxygen sphere, but pulls it more away, creating these dipole moments, which allows then the hydrogen to have a slightly positive charge over here, and the oxygen to have a slightly negative charge, and that's polarity. That's a polar molecule, which will give it some properties. Polar covalence is an uneven sharing. Okay. From, however you want to say it, lower to higher electronegative. The higher the electronegativity, the more sharing it does, the more toys it holds on to and doesn't play. Non-polar covalence is an equal sharing. And remember, there's scales of polarity. Really, the only non-polar bonds are between the diatomics and carbon hydrogen. Okay. Everything else is polar to some degree or another, even all the way to ionic bonds. And in solutions, then remember, like dissolves like. So if you have a polar substance, you need a polar solvent. Okay. Ionic bonding, of course, if you remember from chemistry, there is no sharing. Basically, there's a transfer of electrons. As you form that ion, two elements have such a difference that there is basically a transfer, a pull of an electron from one to the other, because you know what? A highly electronegative element wants to grab an electron, and on the other side, so like here with sodium chloride, sodium doesn't want this one valence electrons, because if it gets rid of it, it'll have a full valence shell below. Chlorine would love it to take that one to fill its valence shell. In transferring that, then sodium becomes positive, chlorine becomes negative, and then an electrostatic charge bonds them together. Ionic bonds are very strong in dry environments, but weak in water. Okay, which is why ionic compounds dissolve and are electrolytes and are very important to all living beings. Remember, there's also weak chemical bonds, and this will be key with some of our macromolecules and DNA and bonding to hydrogen bonds because of that polarity. You can see it here with the water molecules, and one of those emerging properties that allows water solid to float and stuff, and all the different properties of what cohesiveness and adhesion and all sorts of stuff. Okay. Hydrogen bonded to one electronegative element is attracted to another. So these water molecules are near each other because of the slight dipole positive polarity here and the slight negative here. You form a weak hydrogen bond. And that would happen with every water molecule around. Okay. So take a minute and think about bond strength. We have polar covalent, non-polar covalent, ionic. Then we have hydrogen bonds, and we haven't quite talked about van der Waals forces, but they're there. And which is the strongest and which is the weakest. Okay. So I'll let you ponder that, and you can ask that question in class. Okay? Van der Waals happens when atoms or molecules are close together due to electrons constantly moving. And that's why little geckos and things can crawl up walls and certain things. And I may just copy that excerpt for you because it's wonderful. That talks about Van der Waals forces, but really the idea is that electrons are always in motion. So that even in a neutral, even between carbon, hydrogen, and diatomics and whatever, they're not always in the same place. It's not always even, so you can have tiny dipole moments. If you look at the little paws of a gecko, they have all sorts of fine hairs and stuff on that. Or if you think of when you write, it's a Van der Waals moment when you write with a pencil on paper, as you scrape the carbon atoms off because of the unequal movement of electrons, there will be a time when you have a little charge. And so the carbon in the graphite and the carbon in the paper stick together. Okay? You can go look that up, and again, maybe I'll do a poetic reading of Natalie Angier's discussion of Van der Waals interactions. So here's a question to think about. I'll give you the answer on this one because the other stuff you can figure out as to what's the strongest and weakest of the bonds. Opiates, drugs that include opium, morphine, and heroin relieve pain and alter mood by binding to specific receptors on the surface of brain cells. But opiates are not compounds synthesized by the human body. So why does our brain contain receptors for opiates? Think about it, think about it. They don't. Endorphins. Molecular shape influences function, explaining why our brain has receptors that respond to opiates, because the molecular shape is extremely similar. And so it allows those opiates to bind where the natural endorphin pain-relieving hormones would, chemicals would bond. Anyhow, that's a quick run through. As you can see, really out of the chemistry chapter for our continued use, know what ions are, know what isotopes are, be able to read your atomic structure, and have an idea of bonds on whether they're strong or weak. And if you really have to go back here, really covalent bonds are the strongest, then ionic, then hydrogen, then Van der Waals. Right? Okay. All right, there's your quick chemistry look. Have a great day. We'll talk to you soon.